By utilizing TensorFlow Lite, Fast API, and Heroku, today we are going to create and deploy this website entirely for free. You yourself can go to this link and you will see. Please upload your scenes. We'll try to predict which of these categories they are using the TensorFlow Lite machine learning model. So it accepts buildings, forests, glaciers, mountains, seas, and streets. If we choose files and then we upload a couple of them, I'm holding Control to select multiple files. Open, we submit that, it uploads them, and very quickly it uses TensorFlow Lite to run the model on those pictures. It tries to figure out which class they were, and it accurately labeled this as a forest and this is a building, and we can go back home and do it again and again. It is very important to have a project like this on your resume because it shows employers that you know the whole process of not just training a machine learning model, but training it, running all the code to make it useful, actually deploying that, and making it accessible to everybody. So if you found this helpful, I would really appreciate you dropping a like and subscribe if you're not already, and I'm excited to get started. Okay, the first step is to make a new folder. I'm just going to put it on the desktop, but it doesn't really matter as long as you know where it is. I'm going to call it fast-api-app. That's it, okay? Whatever you want there, and then that folder, we should open it and see that there's nothing really in it. We'll fix that shortly. If we go to GitHub, don't look at my private repositories, it's a secret. We're going to do new repository and call it whatever we want. Again, it does not have to match the name of our folder here, but it can if you want. I will call it fast-api-app and just make it copy that same name. I'm going to make it private, okay? So you can probably make it public if you want, but I just want to say as a caveat, it's always safer to do stuff privately, and Heroku, which is going to read from your GitHub repository, does not care that it's private, so go ahead and make it whatever you are more comfortable with. Private is easier, creating repository, and I'm going to do setup in desktop. If you are not comfortable with Git, then I recommend you follow what I do. If you are comfortable with Git, go ahead and do whatever you really want to, okay? So setup in desktop here, that means I have installed the GitHub desktop app. If you do not have that already, go ahead and go to GitHub desktop, just search that in Google, install that, and sign in with Git, and you should be where I am right now. So go to repository, that link, and then local path, we want to choose the path that we set up over here. So our new, whatever folder we made that was new, desktop fast API app, I select that and I clone into there. So that shouldn't really have done too much, but it will have set up the GitHub repository. So what I mean is that if we were to go to, not there, but over here, and then it will make another folder in here, and then we have our .git right there, okay? So that means Git is now tracking the files that are in here, which is going to be very helpful for version control and saving what we've done, as well as allowing Heroku to read from it. By the way, if you followed along with that, but you don't see the .git here, that may be because if you go to view and then show, you don't have hidden items selected. I always do, but make sure you check that. And if you still don't see it after that, then try and redo the process and play around because something must have went wrong. Now what I want to do is make our Python virtual environment. So on Windows, I can go here and type cmd, which in this folder creates a command prompt. So I should have access to Python. If you get an error here, that means you need to go install Python. I am using Python 3.7.9. Okay, so I'm just going to exit bracket there to get out of Python, and then I can type python-m venv.env, which creates a Python virtual environment. It's what we are going to use to store the various Python libraries that our app is going to need. Okay, and it's a very slightly different for what it'll work on Windows versus Heroku, and I'll explain that change shortly. Sorry for the jump there. We do want to activate our Python virtual environment, and we do that with whatever you called it, so .env, and then /scripts /activate, we enter that, and we should see over here .env, which means right now we only have access to the Python libraries that we actually have installed in here, which is really not much. If we do pip list, we should not see much at all. So we want to fix that, and if you were making this tutorial completely from scratch like I was, then you'd kind of just over time add in the libraries that you'd need. But I can make this a lot easier for you. If you were to go to my GitHub and go to the public repository for this, the link is in the description, you would see this file over here, which is two files actually. We have Windows requirements.txt. I am actually just going to take this just like you would. You would copy this code in or download the file. It doesn't matter. You get this, put that in your repository or your folder, and you would do, I'm going to do new file, Windows requirements .txt, and I'm going to copy in all of that. So this is just all the libraries that is going to be needed for running this on our Windows environment, and it is slightly different than what Heroku needs, hence I'm calling it Windows requirements.txt. So now that we have that, we can go in and immediately install all the libraries that we need. Pip install -r, so recursive requirements.txt. That's what it's usually called, but actually it is called Windows requirements.txt. Okay, so we install all of that. It should take a moment, and I'll talk to you after that is done. Okay, hopefully that worked without any errors like mine did. If you did get any errors, hopefully you were able to debug those. And now we have to do one more thing to get this working on Windows. So TF Lite or TensorFlow Lite is a little bit finicky, and so I'm going to go in. You can go to my GitHub again instead of this folder here that you won't have. Windows TF Lite install.txt. This is just a copy and pasteable command that we can run in our command prompt here. So I right click to actually Control V. Now it's a little bit finicky. Let me try that again. Control copy, and then right click that. There we go. Pip install -- blah blah blah, all this stuff, which gets TF Lite in Windows properly. Okay, that is really the slight difference between Windows and Heroku, is that installing TF Lite is just a little bit different. Okay, and it's hard to do it with requirements.txt. It doesn't matter. We should have that now set up in our environment for Fast API over here. I didn't bother moving that file over because we don't actually need that file at all. Okay, with that initial stuff out of the way, we're ready to make our first Fast API app. Going to be very, very simple. So we'll make a new file here, a new Python file. I will call it main. It's easier if you also call it main.py for a Python file. We're going to make that, open that. It uses VS Code for me. That's the editor that I like to use. Feel free to use whatever you want to do. But whatever it is, we're going to write the same code into this file, which is from Fast API import Fast API like this. Okay, notice the capitals, the lowercase here versus the capitals over there. From fast API.responses, we'll import HTML response. Okay, we're going to be returning only HTML really. So to make our first app, which is really just, we're going to make it a variable, app is equal to Fast API like this. So that thing that we imported up here, we're going to make an application right there. So we need to define, if you go to some particular place on the website, what HTML do you want to return? So all of this stuff up here, this actually doesn't matter at all. If we look over here, I actually wrote this slash in here. At the end here, there's an implied or implicit slash, which means if we were to write something like this, at app.get, get means if you do a get, that is an HTTP response type. Don't worry too much about the details. If we put slash here, so if we do a get to slash, that basically just means if you go to the root of this website, if you go to the website here, that is the HTML that we want back. So how do we get back all this stuff? Well, we're not going to get back all of that for now. We'll build that up later. But for now, we are going to get back very simple HTML if we go there. So response class is equal to HTML response. And we'll be returning HTML. And don't worry too much about the async here. You can read about that up about that if you want to. Don't worry. Define main, and then we're just writing a Python function that returns HTML. Sorry, I messed that up a little bit. Main like that, colon, and we're just returning HTML. So content is equal to, we'll just write actually this marquee thing, and I'm just going to copy this over here because I don't really feel it's just a lot of typing and it doesn't really matter. So the important part in here is that I am returning a string. This is a triple quote in Python, so I just do quote quote quote, and it kind of spazzes in VS Code a lot, which is very irritating. But triple quotes, and then inside this you just write a string of HTML on whatever we want to return. And if I zoom out a little bit, you should see a little bit more, which is we're doing a marquee where we're setting the width equal to 525. That's a number I figured out. Where the behavior is alternate. That's just going to make it bounce back and forth. And in this marquee, this is a bouncing. It's going to be bouncing text. We placed in an H1, a header, which is just a big text thing. We set the style equal to, I happen to choose color, which is red. and then font family, I chose Arial, and we'll please upload our scenes. That's the text that we want. For H1s, we do a backslash, or actually that's a forward slash H1 to close that tag here. So here we open it, we specify what is in there. Between the two tags, we place our text, and then slash H1 like that, and slash marquee, which closes our marquee over here. Okay, so I just made some intro HTML there, and I copied and pasted rather than typed it out. And we just need to return this content. Okay, so we return content, which should know that if we go to slash and we return the specific HTML here, then, well, we're going to get back that HTML. Let's hope that we do. So how do we run this application? Well, in our virtual environment, that's important because otherwise we wouldn't have fast API, which is what we're going to need right now. If we do UVcorn, that's also something that's in our requirements file. UVcorn main, that's the file name that we have here, main, and then app. Okay, so app here and app.get, that's how we know it's app. If we run that, then we should see it spins up this weird looking thing. It's running on this website. It looks like a website, but really this is only accessible locally. Okay, so this is just a local web server. And if we go into Chrome and type that, we should see we get very close to the right thing. We get a quote. Clearly, there's a small error there. But yeah, we get please upload our scenes with the bouncing back and forth text, and that's fine. So that's our first app, and for now, actually, we're going to leave the fast API code to later. We have a lot of work to do, first in training the machine learning model that we'll be using to deploy our app and write up some functions there, which we're going to do all in Colab. So I'm going to get started there. By the way, if you're looking to fix that small quote error, I think I just had one too many quotes here, and so it was showing that on the screen as well, and you can see I fixed it up here. Okay, I just magically set up a Google Colab notebook. If you're not familiar with Colab, you don't technically have to use it. It will be helpful to follow along with this though. At least I have the link in the description down below if you want to see the one that I have that's all done. Okay, so go to Google Colab if you are following along and create a new notebook. And also you have to make a Kaggle account. Okay, so kaggle.com, you have to go to make an account here and generate an API token. So if you go to account over here, I'm going to skip over quickly, you can create a new API token and that will download a kaggle.json file to your computer. We're going to need that because we're using a dataset from Kaggle. And I'm just going to copy and paste this. This is probably the only piece I'll copy and paste because it's just kind of boring. Upload Kaggle.json API token, so make sure you go and do that. I'm going to do that right here. This basically says, where is it? Where is my Kaggle file? I'm going to search for it. Kaggle, there it is. Kaggle.json API. So what that does is basically just tells Kaggle that you have an account and you're able to download this data set right here. So we're going to make this directory called tilde/.kaggle. We're going to copy that kaggle.json into that folder we just created. And we're going to change the modifications and Kaggle datasets download -d Puneet 6060, thank you so much for this Intel image classification dataset. And I will show you what dataset this actually is. Hopefully, if I just search this, it'll come up pretty easily. Yes, it will. And here's the dataset that I'm going to be using for creating the machine learning model that we're going to be deploying. And it's not amazing. Like it's kind of simple. It takes buildings, forests, glaciers, mountains, seas, and streets, and tries to classify each one of those. It's like a medium difficulty. It's going to need some sort of a convolutional neural network probably to do this well, or maybe more advanced techniques if you're down for that. Anyways, we're going to download that with Kaggle and then unzip Intel image classification.zip. It should all run as long as I have that file up here, and it should make Intel image classification.zip. It's downloading a little bit. And the good thing about Colab is it doesn't actually matter what your internet speed is. My internet speed here isn't very good, but since this is actually just activating a cloud environment that's downloading stuff onto that cloud environment, the internet's very, very fast. And so it did that quickly. Anyways, after we unzip that file with at the top here, I'm just going to close this, unzip Intel image classification.zip. It should have a few folders here, segpred, segtest, and segtrain. I assume the seg is for segmentation, but I don't really know why they needed that. Okay, so this is going to be our training data set, and I'm hoping that you're somewhat familiar with training machine learning models. That would make this a lot easier. If you're not, then enjoy following along and trying to grasp but you can, because I will try and explain it as much as possible. Either way, you don't actually have to watch the model training either. If you want to skip over this section and just go to actually deploying the model, that's totally fine too. But we have a training set, which is what we'll use to train the model. It actually has this annoying nested folder thing where it's just the exact same folder in that folder. And then we have our categories. So buildings, forest, glacier, mountain, sea, and street. And in each of these, we have a fair amount of photos, and we'll actually count how many photos we have for each of these. Okay. So these are, with some exceptions, generally, it is 150 by 150 by 3 images, meaning they are height 150, width 150, and the color channels is RGB. Okay, so we'll see that shortly when we import them into NumPy, and we have that for all the buildings in train, and we have that for prediction and test. I don't think we use prediction, I'm not sure. We are going to use test for sure to test our model. Okay, so we have that, we have our data set up now, and let's go pretty much take a look at that. Okay, so we are going to load a sample image from the training set with import CV2. Luckily in Colab we already have that. Installed. So that's OpenCV Python. If you're not familiar with what CV2 is, it's for dealing with image data. Building is equal to cv2.imread. So we're reading one of our files. We can read this with segtrain. As you saw, that kind of double segtrain thing, segtrain slash segtrain slash we'll read a building. So that's buildings slash just one of the files happens to be called 10006.jpg. Okay, so that is building. That actually reads it into a NumPy array. Building.shape. Shows that it is 150 by 150 by 3, as I said. Height is 150 pixels, width is 150 pixels. We have 3 color channels, R, G, and B. Now we're going to visualize the building. For some reason, Colab has a slight CV2 problem, but they actually have an easy way to get around this. From google.colab.patches, we can import cv2_imshow. And then if we do cv2_imshow building, that is going to show the image right there. And it's beautiful. It's a nice building. That is going to be one of the classes that we're trying to recognize. We're going to make a machine learning model that is given these input-output pairs, where the input is a building, this picture, and its output, we know that it's a building by the label because it's in this file structure right here. We know that this is a building. We know it's a forest, and this will be used by the TensorFlow Kira's image generator very shortly. We'll just visualize one more just for fun. We'll do a forest is equal to a cv2.imread, and feel free to look at whatever you want to. This is just 2 examples. Segtrain slash forest slash 10007 happens to be one of them. There we go, 7.jpg. That's a forest as a NumPy array. We can do cv2_imshow as before with the forest, and we output there's our pretty forest. Now that we've done some visual inspection, I want to just get the class folder paths, which is the full paths to the training set in each of the folders. So segtrain slash buildings, and then that plus build forest, glacier, and if that didn't make sense, don't worry, I'll show you right now. Class folder paths, we're going to get this is equal to the list of segtrain slash and then plus x for x in the os.list.dir, so that lists the directories given some directory. Segtrain, sorry, I'm going to close this so you can see a little better. Segtrain slash. Okay, this is a very long thing, but basically you can see here for each item in the list, it's going to start with this, and then it's going to add on this os thing, which we actually have to import os. And it's going to add on the list directory of this piece right here, the full thing, which means we get class folder paths is equal to this. So why do we care about these paths here? Well, I want to actually go through each of these paths and count the number of items, because if we pass this to if we pass that to os.listdir, I will show you an example. If we pass this whole thing to os.listdir, then that goes through and looks at all of the files or all the pictures that are in that individual folder. And if we get the length of that, so the length of this, then we can see that is 2404. I'm going to print all of those counts in a prettier way with this function here. So now that we have these class folder paths, I will do, sorry, just let me scroll for a second, for class folder path in the class folder path. So I'm just going to iterate over that thing we just created. And then we can do a nice pretty print, which is print. We're going to format it by doing this this curly 0 thing. We have to pass that a variable, which we will shortly. Here's the variable. We'll pass it after we do dot format. We pass class folder path. Class folder path. Okay, so that's going to just put that in there as that 0. And then colon, what do we want to show as well? We'll do comma and then length os.listdir with the class folder path. Okay, so that's as we just saw the length of that folder path. If we get the length of this thing, that's how many items that we have in it. If we iterate over it, we can see here we have 2404 in Glacier, 2071 in Forest, and around a little over 2,000 for each of the classes in the training set. That should be more than enough to for this relatively simple problem to try and learn a function or a deep learning model that's going to take an image, it's going to take a glacier, and hopefully if we feed it enough of these input-output pairs where the input's a picture and the output is which category it is, hopefully it'll be able to figure out which class it is over time. Okay, so now I'm going to store 2 variables, which I'm going to put in capitals because they're basically constants, but it doesn't really matter. Train dir for train directory is segtrain /segtrain /segtrain/. Okay, so that's the training directory, which basically it means it's the folder, the place where it starts. It has all of these different categories. So it's this and then this. It has buildings, forest, glacier, mountain, sea, street in those. Then we're going to get valdir. So basically validation, you can basically call it test because we're not going to be splitting it into three different folders or 3 different splits of the data. Basically, we're only going to do 2. Segtest /segtest. And don't really worry about that pred thing for now. Okay, so train dir and valdir are going to be those constants, which are the paths to the training and the test set. And then we can make our generators, our TensorFlow Keras generators. Let me talk about this. So from TensorFlow.keras.preprocessing.image, a lot of big import there, import this image data generator thing. And what this does is it's going to go over automatically and basically grab the images that are in here when it needs them. And so it's not going to just throw all of this data into a big NumPy array and store that in the RAM, because that would absolutely kill the memory performance if we were to do that, because we have so many pictures. So this is meant to iterate over this and grab what it needs. If that didn't make sense, do not worry too much about it. It doesn't really matter. Train data gen is going to be an image data generator, that thing we imported, and then we can add in whatever augmentation here. So it shows here all these different things. And this is because for images, we can very easily make a bigger data set if we wanted to by doing stuff like shearing. That's an adjustment we can make to pictures to increase the training set. We can zoom all the pictures and look in a little bit. We can shift the brightness a little bit and shift the height and rotate images. This is all sort of data augmentation stuff, which I really don't want to cover too much in this video. I'm just going to set horizontal flip equals true, which means for basically we'll add in a % chance that for each of these forest images, actually we saw one up here, this is still a forest, even if we kind of flip it around. If we flip it upside down, the trees would be upside down, and that wouldn't look quite right, but it might be okay. If we were to flip it horizontally, then it should still be a forest, and so that's a good idea. And all that other data augmentation stuff is not a bad idea at all. Okay, so we are going to. No, I don't want that. We would get train generator. So it's kind of weird. We have to do this generator twice. Train generator is equal to that train data gen thing dot flow from directory. So here we have the information all in our directory, so we can do this. We'll pass the directory to that. So train dir, we define that above. We will also pass the target size, which is the size of the images. So that is going to be, we don't need to add in the 3, so it's 150 by 150. That's what they are, as we saw. And we can do color mode is equal to RGB. All right. So red, green, blue, they are colored pictures as we saw. We'll set the batch size to be roughly 32. So that means we can pull 32 images into memory, or roughly 32 at a time. You can play around with the number if you want and set shuffle equals true. Because it's a training set, we probably want to shuffle the data around. For the test set, I don't think it even really matters, but we are going to set shuffle false for val generator. So I'm going to copy most of the stuff. Actually, I will copy it from my other notebook because it is going to look extremely similar. Val data gen is this image data generator. We do not want to do horizontal flip, and you probably could get away with it, but for just validating the model, we're just going to leave the data as it is. Full from directory, we'll pass it to validator. I'm going to change the formatting a little bit by just tabbing backwards a couple times. So we pass the validation directory as we saw over there. Target size is still 150, 150. Color mode is still RGB. Batch size is still 32. Class mode is categorical. Okay, we should actually have that for the one as above as well. I think it's the default, so it probably doesn't matter, but we should add that in. Shuffle, that's complaining because of a comma. Shuffle will make that true, and shuffle false for the val generator. Hopefully, if we make all of this run, it gets 14,000 images belonging to 6 classes for the training set, and 3,000 images belonging to the test set. Okay. So now, something very important is that generally when we set up a data set, if we were to do it like in NumPy or something, you would have the labels corresponding to each of the inputs. And we still have that, but it's kind of buried in this folder structure here. Luckily, Keras actually knows that when you're to train a machine learning model, it can automatically correspond indexes to particular classes. So if you don't understand what I'm saying, just watch. Labels is equal to train generator dot class indices. And if we were to output labels, get out of my face, I know, labels, we can see buildings is index 0, forest is index 1, glacier is 2. If we were to just flip this around, we can create something, we'll do call it a class mapping. Class mapping is equal to the dictionary of, we'll do v and k, that's just value and key rather than key value, because we're trying to flip this so that we can get an index corresponding to the class rather than the other way around. V and k, for k and v in labels.items. Okay, it's a dictionary, so we'll go to the items and just see that class mapping is now the reverse. This is what we really care about, because when we make a machine learning model, when we make a deep learning model using this generator thing, it's going to output basically in order different probabilities for each of these indexes. So the first index will be the probability that it thinks it's a building. The second output will be the probability it thinks it's a forest, which we can access through index 1. The third thing it'll output is the probability it thinks it's a glacier, and so on and so on. We'll see this shortly. If that didn't make sense, do not worry too much about it at all. Okay, so now we can define our machine learning model, and this is absolutely up to you. I just wanted to make a very quick model, or like quick as in inference wise, a very fast model. As you saw when we pinged this this website here, it responded very, very quickly. It ran the model however many times it needed to, and it gave our responses within a blink of an eye. So it did that partly because I chose a fairly good machine learning, fairly fast machine learning model. The trade-off is that maybe a bigger model might get more accuracy, but it does quite fine actually. So from TensorFlow.keras.applications, we'll import MobileNet v2. So that's the model that we chose. It's very well known for quick inference, but also pretty good for classifying images. From TensorFlow.keras.applications, we'll import its preprocess input function. We'll see more about that shortly. MobileNet v2, import preprocess input. Okay, sorry for the jump there. I was just being weird about the import. That is how to import the preprocess input function. We can do from TensorFlow.keras.models. We'll import the sequential model. Okay, I prefer to use sequential if we can. It's a lot easier. From TensorFlow.keras.layers, our final import here, we will import so the various layers that we're going to need. We're going to need an input. We're going to need a lambda, which is going to help call our preprocess input function here. Input lambda will do a global average pooling 2D. If you do not know the specifics here about what's going on, it doesn't really matter. I will show you a summary of the model, but don't worry about it too much. Okay, and a dense model. So how do we make this model? Well, we will do before MobileNet. Okay, so before this is this whole chunk, this whole MobileNet model that's already pre-made basically. What are we going to do before that? Well, before MobileNet, we will do a sequential where we do an input. We specify that we get a 150 by 150 by 3 image, and then we will do a lambda, where we call the preprocess input function. This is all that it has to do. And so what this is saying is we get in a picture, and then we automatically apply this preprocessed input function. MobileNet requires, and each of these kind of pre-trained model, technically what we're doing right now is called transfer learning, by the way. We'll see this shortly. So each of these different functions that we, or models that we have, require some particular preprocessed input function. And so we just take the input and we call that particular preprocessed input function, and then we can do MobileNet. So MobileNet is equal to a MobileNet v2. I'm just calling this thing that we imported up here. And then we need to specify very little, actually. We say that the input shape is still going to be 150 by 150 by 3. 150, 150, I don't need two brackets. 150 by 150 by 3. And then include top is false. We do not want that final layer, and we'll see why in the summary. Then after MobileNet, what are we going to do? Well, it turns out, and I don't want to worry about the specifics too much, after MobileNet, we are going to do a couple things, which is first, as we saw, this global average pooling thing. Global average pooling 2D, and we call it like this, bracket, bracket. That is pretty much does what it says. It has normally this 3-dimensional input, and it's going to do a huge average to shrink it down into a 1-dimensional thing. After that, we can do a dropout, which is good for fixing overfitting problems. It makes the model better. 0.3 is probably an okay number. And then this final part is probably the most important to understand other than the input. We're going to do dense 6 and an activation. Activation is equal to a softmax. Why are we doing a softmax? Well, this is where we want to output a bunch of probabilities, or basically a probability distribution according to what class it thinks it is. So it takes in an input. We want to output the probabilities of all the different classes that it could be. And we'll see what it outputs very shortly. Okay, so then we just need to define what our model is. Our model is the sequential of whatever we're doing before. So before MobileNet, and then we do MobileNet, and then we do after MobileNet. That's why I called it like that. And then we can, it's with this lambda layer that we used, it's slightly annoying to do a summary, and we'll see this, we'll see how to fix this. It's not difficult. Basically, first we're going to compile the model. And so do from tensorflow.keras.optimizers. We'll import the Atom optimizer. It's pretty much my go-to and a lot of people's go-to optimizer. Or opt is equal to the Atom, where we set the learning rate. This is definitely a function that you, or a value that you might have to play around with. I found that doing 0.00001 is pretty good. When we do model.compile with optimizer is equal to that Atom optimizer, and set the loss equal to, this is important, we're doing a categorical classification, categorical cross entropy. And then metrics is equal to accuracy is actually fine. Why is accuracy an okay metric? It's because we saw that our classes, they have roughly all the same number of inputs, so accuracy will be slightly biased towards the ones with bigger examples, but it's really close to a proper metric, so this is totally fine. Okay, we can run that cell, and then we can build the model so that we can summary it. And I'm just going to copy and paste these things because this isn't really important code. We model.build, where we set the batch to be none, 150 by 150 by 3, and then before MobileNet.summary, MobileNet.summary, and after MobileNet.summary. So if we were to go through this thing to explain what our model is here, sorry, it's the Colab output's getting finicky. So first, we can see 150 by 150 by 3. That's what our input, it doesn't show it, but it's there. And then the lambda gives a 150 by 150 by 3 with no parameters that are going to be trained at all. It's just taking an input and applying a preprocessed input function. Then we do all the mobile net stuff. And so it takes in 150 by 150 by 3, does a bunch of convolutions, patch normalizations, depth-wise convolutions, all of this fancy stuff that doesn't matter too much. And it goes through a lot of different layers. And then at the very end of it, wow, it keeps going and going and going. And then at the very end of it, after, 16 blocks, we are going to get this 5 by 5 by 1280 thing. We want to convert this into eventually just six nodes or 6 outputs. And so what we do is a global average pooling, as we saw, which takes it, basically it does an average where it gets rid of these 5 by 5 things and it just replaces it by 1280. It gets an average for all of these 1280 5 by 5 things. And then we are going to convert that to 6 outputs. And this is what our final output is. It is going to be a probability distribution. And so it sums to 1, all the different outputs. The first output is going to be the probability of getting that first class, which we saw in the dictionary. The probability, the second output is the probability of that second class in the distribution, and so on. Okay, so that is our model. We have not trained it yet. It is not difficult at all to train it. To do that, we are going to first make a model checkpoint. So from TensorFlow, TensorFlow.keras.callbacks, we're going to import model checkpoint. And so this is for saving the model so that we can actually just kind of close. We can just cancel the operation and it will be saved with the best one that we want. Model checkpoint, where we specify the directory, model / is totally fine, and save best only is true. Okay, so this means that it's only going to save, write a save file to that model directory if it is better. If this epoch, which just means a run through the data set, we're going to do 7 epochs or 7 runs through the training set. It's only going to do that, save at the end of every epoch if the newer model is better than all the previous ones. Okay, so train CB checkpoint is that, and then we can do model.fit, where we pass the train generator, which we defined above. Train generator, we can make the validation data equal to the val generator, which we defined above. We set the callback, so this is what it does at the end of every epoch, which we specified was the train CB, the train callback, and epochs. It happens to run, or I happen to know that if we run it for 7 epochs, that's probably going to make a pretty good model for this. Absolutely, if you want to play around with this, or for some reason it doesn't work out well for you, then feel free to play around. But basically, this should start the training process with the first epoch here. Out of 7 of them, I may or may not cancel it early because it will be saving to model / over here as we go. But just to make, I'm going to stick around to make sure that this actually gets started because it's taking a moment. And come on, anytime now. Let's go. I think it's going, but you just can't. There we go. Okay, so 20% accuracy. This will steadily go up as I have a pretty slow learning rate. And if I had a faster learning rate, that would probably make this increase faster, but we might not get as good a model overall. And yeah, so I'm just going to talk to you again at the end of the epochs, and I'll tell you what I did about that. Sorry, this is important. I actually forgot to say this. Make sure that if you are doing this on Colab that you have your runtime as a GPU environment, or I don't think you can use TPU. If you can, that's pretty awesome. But GPU should be fine, which will very dramatically and possibly just allow you to train this machine learning model on Colab itself. Okay, you probably would have to rerun all of the stuff from above. So what I would do if you were in a CPU environment by default, factory reset the runtime and just do all the steps above. You don't have to write all the code again. You would just have to upload your Kaggle file and run all those cells, and it should work just fine. Okay, sorry about that. All right, there's a lot of stuff on the screen now, but the important pieces are each epoch, something happened. We got some accuracy on the training set, which is just accuracy. And we can see TensorFlow assets written to blah, blah, blah. If I was to scroll over here, assets written to model / assets. Okay, so we can see here model, and here there is all the saved model stuff here. It is actually not finished yet, but we have gone through 4 or 5 epochs now with a validation accuracy. That's the one we care about. That's accuracy on the test set, basically, on information that it hasn't seen in training, which is what we want. If we're getting accuracy of about 90% on data that we haven't seen before in training, then we're pretty much happy. So feel free to make this a better model if you want to keep training yours, but I'm going to just cancel this. That's totally fine because it is already written the best model to this model assets right here. Okay, remember that this is Colab, what we're using right now, and it likes to just kind of delete our files quickly sometimes. So you want to zip-r model.zip and then model slash, which basically just says, okay, in this model slash directory right here, I want to turn that into a zip file, and it's going to do that pretty darn quickly. Deflated 79%, blah, 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 and it's added all of that to the model.zip here. And that's important because we can't really download files. We have to zip stuff first. We download that model.zip file. It's on my computer, at least my internet here, it is a little bit slow, and that is a limitation for sure, but it's not too bad. And once that starts to download, by the way, the file size is completely dependent on, or at least mostly dependent on the model that you chose. So we did MobileNet, which is pretty small. If you were to choose a different model, like Exception is a bigger model, which will probably do a little bit better. They were made at pretty much exactly the same time. That would be a little bit bigger, and it would run a little bit slower. It would take up more space, but that would work as well. And I'm really just talking to fill time while this downloads, and it looks like it's just about done. That's actually just the preparing process, and then it downloads very quickly. So here we go. It should see it. If we go to show in folder, we should see model.zip right there. And now we can extract this and put this in our folder that we have for our app, because we're going to need this for our app very shortly. JK, we're not. Okay, we are not going to use this. Why is that? Because this is the model for loading it in Keras, or TensorFlow Keras, where TensorFlow is this massive library. Okay, we don't want to use all of TensorFlow. That's why we're going to use something called TensorFlow Lite. It's a lot better. So how do we do this? We are going to import TensorFlow as TF. I know it's kind of weird because we are already using TensorFlow, but we're going to explicitly import TensorFlow as TF. We will make a converter. So now we are going to convert this Keras model into TF Lite format. We need TensorFlow for that. Converter is equal to tf.lite converter dot from Keras model. Keras, I always say Keras, it should be Keras. From Keras model, and then we called that model. So what this does, converter is TF Lite converter from Keras models. We pass in that model, and then we can do TF Lite model is equal to converter.convert. Bing bada boom. If we have that, we can see TF Lite model is something that doesn't really output very well, but we need to save this to file so that we can actually read this. And what we'll notice very shortly is that it's going to be a very, very small file, which is awesome. So it's going to be extremely lightweight, and you could deploy this not only on web applications. It's easiest if we do, for a web application, it's easier if we do TensorFlow Lite, although we might have access technically to something as big as TensorFlow, but especially if you were doing like making an Android app or deploying this on some sort of like actual robot, then you would probably need it in this TensorFlow Lite format for that very tiny file, for that very quick inference and just lightweight work. Okay, so we have TF Lite model here. Looks like it's almost done. This is kind of a bit of a slow process, but we do with open and then model.tflite. This is the file name. It's important that it ends in tflite because it is a tflite model. We will do that right back as f, and then we'll do f.write with tflite underscore model. And that is not quite ready to do yet. It will be after this is finished, but looks like I'll talk to you after that's done. Okay, sorry, I had a tiny collab error, but basically the point is that we save this model.tflite file. It should show up over here, and then you should download that as well, like I did right there. Now that we have this file, it should show up in downloads. So if I was to go here, and then here's all the videos that I'm creating as time goes by, if you care. Downloads is model.tf right here, And if I open up these side by side, I should be able to place it in. What we're actually going to end up doing is putting this in a static folder. So I'm just going to put this here right away. Static folder in our Fast API app. I'm going to move model.tflite right into that static folder. And we will soon, when we go to make the Fast API app, then we'll be able to use that model there. So for now, in Colab, how are we going to use this model? Basically, if we haven't imported CV2 already, I'm going to do that. I'm not sure. Import CV2, and then import numpy as NP. So if I read in, we'll say 2 images so that we can see how we deal with multiple inputs. Input 1 is going to be the CV2.imread. We must have imported CV2 already, but that's fine. We'll get it from the test set. So segtest/segtest/forest. So here's a forest, and then we'll go with, it happens to be that 20056.jpg is one of the pictures there. And we will copy and paste this, basically exactly the same thing, but for another forest. So this 20, basically just change this to 62 at the end. And this should be, hopefully if we run that, yes, okay, so that all worked. Now, let's first just make this, make a list of both of them. So we'll say inputs is equal to the list of input 1 and input 2. Okay, and then we should see that inputs is these 2 things here. Note that this for now isn't actually a NumPy array, it's just a list of 2 different NumPy arrays. So we're going to visualize, I chose the second input because it just looks a little bit more obvious to illustrate this point. Import matplot.pyplot. Why am I not doing lib? Matplotlib.pyplot as plt. And then I will do a plt.imshow with the second input here, so inputs 1. If we do that, we see a forest, kind of, sort of. The problem is that actually matplotlib and most of NumPy, actually, pretty much every library except OpenCV reads images, assuming that the order of the channels, or basically the 3 different pictures that you have, because I said it was 150 by 150 by 3, what most of them assume is that it's R, then G, then B, red, then green, then blue. But for some reason, OpenCV is a little bit different, and it assumes images are in BGR, so blue, then green, then red, rather than red, then green, then blue. So what we need to do, and what we're going to need to do for our app as well, is get all the inputs and we convert color. So cv2.convert color. There we go, convert color with image, and cv2.color, this is just a bunch of constants, color BGR to RGB. Okay, so it's in BGR by default. We're changing it to RGB, and we'll do that for each of the images in this inputs thing. So we'll do that to all of them, and that's overwriting inputs automatically. It doesn't seem to like this, but I'm pretty sure it will soon. And inputs should be totally fine. There you go, same thing. You won't really tell a difference in the input, but I guarantee you that it switched the channels around. And then we can do plt.imshow with inputs sub 1. Again, it did it for both, but here, this is actually the exact same picture, except you can tell this looks a lot more like a forest than the other one does, at least in my opinion. The sky looks really messed up here, and especially the ground does not look right. This looks much more like a forest, and that's going to be handy because our Keras, our deep learning model, assumed that it was in RGB. If you look above, if you look over here in our generation set, we said color mode was RGB, and I don't think we can do BGR. So we did RGB, and so we have to convert all of our images. If we were to read them in with OpenCV, we have to read them, convert them to RGB. Okay, so that's just an illustration of that, and hopefully just kind of helped with computer vision in general, because this stuff comes up a lot. So let's now make this a NumPy array. So inputs is equal to the NumPy.array of inputs, and then inputs.shape. Inputs.shape is then, we have 2 images, 150 by 150 by 3. Now let's use our model. So we haven't actually really loaded our model yet. So we're not going to use the TensorFlow model because that doesn't really help us. We are going to load up the TensorFlow Lite model. So how do we do that? Basically, we need this TF Lite thing. So on Colab, it's a little bit easier to do this than it is on Windows. I forget if yeah, actually we already installed TensorFlow Lite on Windows, so you know that. Pip install pip install tf-lite runtime is actually all that we need. I don't think it's there by default. And then it starts to be a slightly weird from here on. For me, this was actually my first time using TensorFlow Lite. It took a little bit of time figuring out, but I think I have a pretty good handle on it. If we do import tf-lite underscore runtime dot interpreter as tf-lite. Okay, so just pretend basically we have access to tf-lite with this thing right here. So interpreter, it's actually really just the model. So I'm going to start calling it model. Model is equal to tf-lite.interpreter, interpreter with model.tf-lite. Okay, so that file, as long as that file is in this directory we're passing it here, model.tf-lite, then it should be able to read that in, and we shouldn't see any errors if we were to do that. Okay, so that's all good. Now, there's a couple things that we need to do that just look a little bit different than using it in normal TensorFlow. We could do interpreter, or we actually have to do interpreter.allocate tensors. I don't know why they made you do that, because you have to do that every time, and it doesn't even change, but you have to allocate tensors. And then we get the input details is equal to interpreter.get input details, bracket bracket. If we check what the input details are, we can see here. This is, no, it has no attribute interpreter, right? That's, sorry, I meant to write model instead of that, model.allocate tensors. Here, I don't know why it was writing that again, so sorry about this. This should have been model as well. And so here, we get the model as the interpreter, model.allocate tensors, get input details, and then here, ignore most of this stuff, but it's important that actually it's going to take in a float 32, which is not entirely expected, because what images generally are, if we saw the input as above, if we were to look at just inputs 0 for a second here, we can see that the images are really a bunch of integers, but our model, our TF-Lite model, is going to expect floats. Okay, so we need to remember that, because we'll have to do that conversion, as well as the shape. We can see it's a 1 here, so it really only accepts these 1 images at a time, and it's not just 150 by 150 by 3. We actually have to just do this weird reshape where it's 1 by 150 by 150 by 3. Okay, so this is a bunch of confusing stuff, and it doesn't really matter too much, but just getting you into trying to understand TensorFlow Lite if you were to do it yourself. Output details is equal to model.get output details. We need this too. Get output details, and output details are what? It looks very similar to this thing. We can see technically it's also this list with one item, which is a dictionary. And its output is, ignore that, where is it? Shape is 1 by 6. This is what it's going to output. Why is it 1? Couldn't tell you. We could just get 6, and it's going to be integers. We'll see what it actually outputs, okay? So this is really weird. TensorFlow Lite is weird. Let's ignore all of this stuff and just start using it, okay? So how do we use it? Well, I'm just going to copy and paste in this function for you and explain it, because it is a little bit confusing. We're going to define model predict, which takes images array, and that's going to be a NumPy array that looks like this. Okay, I looked at the shape here, inputs.shape. It'll take in something like inputs here. So predictions is the length, the list of 0 times the length of the images array. So I'm just initializing all these predictions to be 0. We're going to enumerate. So if you haven't seen this before, for I and val, and enumerate the predictions, which is, so all of the vals are going to be 0. And so if we were to do a control search here, val actually doesn't show up. We could have done it for I and range, but I just chose this. So ignore val. For I and val and enumerate predictions, we'll make the interpreter. So interpreter, we don't have that thing yet. This is actually called model. Okay, so I'm just going to do a paste here. This is going to be model. This is going to be model as well. And this is going to be model as well. Okay, so model.set tensor, we need to set each tensor or input basically before we, well, that's what passing it in is, okay? So we do input details sub0 sub index. That is this input details right here. Sub0 means this dictionary, and then index, that is, there we go, 0, okay? So don't worry about that too much. But images array sub I dot reshape 1 by 150 by 150 by 3. What the heck is this thing? Well, that is taking in our image. So each of these should be an image. If we iterate through the predictions, we would have I, then we get images array sub I. That'll first be the first image, then the second image, and so on. Each of those are 150 by 150 by 3s. We need to reshape that into 1 by 150 by 150 by 3. Okay, so we don't actually really set a variable here for getting the output. We just do model.invoke. It just means run the model. So we set the tensor according to its input, and then we reshape and we pass in the input that it needs. We run the model on that tensor, and then we do predictions. So by is model.getTensor, so that's get the output with specify the output details, and then we need to reshape that into 6 because we don't really want that 1 by 6 thing. It's just kind of irritating. So then after that, the prediction probabilities is the array of all the predictions. Let's not worry about that for now, and let's actually just make this return what predictions is. So that's what that's after all this stuff, return predictions. How can we call this? As we saw, model predict with we have this thing called inputs. Here you go. Why is this not happy? Got value of type uint8, but expected type float32 for blah blah blah. Okay, so as we saw before, we were trying to pass it in integers, and it actually expects, or here it expects floats. So we do not want that, but we can fix this very easily by doing inputs dot as type. This is a way in NumPy to convert NumPy arrays to a different data type. NumPy inputs dot as type, and then NumPy dot float32. So we convert that input to float32 first, and then we call model predict on that, and then it's happy. It returns this list of 2 items, which this is just predictions for now. It's all of these different probabilities. All of this actually would technically sum to 1, which looks a little bit weird because the output is very weird. But basically we can see that this number is, it looks small, but it's much bigger than all of the other ones. This is index 2. If we see it, this is well, the second spot basically. It's index 1, but the second spot. So 0, 1, 2, 3, 4, 5. And this one as well, 0, 1, 2, 3, 4, 5. So it thinks that whatever's in the second spot, or index 1, is what this class is for the first input. And it thinks that as well for the second one. This is the biggest value. It's the one with the highest probability. If we look back, what does that actually mean? Well, we made this thing called class mapping. So it thinks that it's this index 1 here. It thinks that it's a forest. We can do that, grab that automatically. If we were to do class mapping sub, let's just do, if we pass this in, actually, no, I'm not going to do that for now. But basically, we know that if we were to get the argmax, okay, so first we convert this to a NumPy array because this whole thing to a NumPy array, just because. And then we do argmaxes on access equals 1, which really what that does is that converts, okay, all of these inputs here, this just returns this index 1 here because that's the maximum argument. Arg is the index 0, 1, 2, 3, 4, 5. Arg max is 1 here. That would return 1. And this, if we do the same thing here, this would return a 1. So if we were to return just the argmaxes here, and that's really what we had at the beginning, if we return the argmaxes, then that returns 1 and then 1. All right, so that is saying that the first one, it thinks it's the first index. The second one, it thinks it's the first index as well, which all makes sense because these inputs that we were reading in were these forests. It means it got it right. Okay, so that was a little bit confusing, but that is the main application logic that is going to be thrown into our fast API code. So this is the section where basically all of the model stuff is done. We trained the model, we made it a TF Lite file, and this is the function that we might have to adjust it very slightly in fast API, not sure, but that's all of the stuff that we've done around the model, around training and around inference. And so now we just need to put this into our fast API app, make it so that we can upload images, make it so that we have pretty HTML, and actually run the model on the pictures that they sent us, return back the HTML that we want to according to that, and that after we deploy it, we will be done. Okay, back in our main.py file for our app, we're going to start adding to this, and actually we're just going to keep adding to this until we are done, basically. So one thing which I just kind of copied and pasted, or now I'm going to paste off screen here, which is this head HTML thing. So this is just basically a big string for the top of what's going to be used at the top of our HTML files. We'll actually have to use this twice, hence I have it as this variable outside of the functions here. So all it is a head with a meta name is viewport, and content is equal to width is equal to device width, initial scale is equal to 1. I will again go and zoom in so you can see that a little bit better. Okay, so we have that, which basically all this does is it specifies that if you were to view this on a mobile device, it would make it look much better without a whole lot of effort into it. Okay, so then we have a body style is equal to background color powder blue. That's how I have that nice pretty blue color, and we're also going to just by default center everything that is below. Okay, so we're going to do that, and then we'll simply make up here, we'll do content is equal to head HTML plus that string for now, and then we will return content. If we were to, so I have to go here into our command prompt. I actually kept this running, wouldn't be surprised if you closed it, but basically you close it with holding control and then pressing C a couple times, and then you should be able to just press up on the keyboard to rerun the exact same thing, UV main:\app, and then we can do a HTTP call. We copy this over, and this is the website one, but over here we should just be able to update this, and here we have the pretty blue, it's centered, please upload your scenes. And if we were to go to this, it's kind of hard to go to this, or impossible to go to this on a mobile device right now because it's just on our local computer, but if we were to deploy that, it would look better on a mobile device as well. Now I want to start to make this table that we've seen here, and you might not even have known that it's a table, but if I hit F12, we can zoom in on our web page, and I can see here table align center, table body, and then TRs, a bunch of TRs. In each of those TRs, which is a table row, you can see it's highlighting the whole row. Each of these, it has these table data things. Here's a TD, which is that image, and then another TD, which is the label corresponding to it. Another one, table row, is that picture, and then it is the label corresponding to that picture. Okay, if we were to go to submit a couple images and do this next page, which we haven't made yet, we will see these here. These are column labels for the table. So first we will see table body. In the first table row, these actually aren't TDs, they are THs, but it's really pretty much the same thing, table headers. And then after that, each table row is going to have, again, an image and then a text with so there's the path to the image and then the text corresponding to it. So we're going to try and build up this table thing. And there's two main ways to do this. One is to generate our own kind of automatic Python generator. The other way is to do something called templating. And we're not going to do templates here because our HTML pages are not going to be overly complicated, and I want to really explain what Fast API and if you see Jinja syntax, this templating thing, what it's really doing. And all it's doing is just returning some specific HTML. So we're going to generate all that without doing the template thing. I just copied in pasted in a function, which is going to make pretty much the tables for us after we figure out how to call this function, which we're not going to worry about quite yet. So this function, getHTMLTable, which pretty much returns the corresponding HTML for this whole table thing, corresponding to this, anything under this table pretty much. So what we do is we pass it image paths, which is going to be a list of all of those paths. So you can see here the first image. If I was to look at that, tr, there's the header, but if I go down here, so here, this is the first image path, /static/mountain. This doesn't actually exist in our folder yet, but if this did, then there's a way for us to show the specific path to actually display the image, and I'll show you that in a little bit. But for now, just know that this is the first path in image paths, and then this would be the second path in image paths, this path right here, this source. So we store all those paths, as well as each of the corresponding labels, what we want to pass with that. So we have two options there for our function to make this table, all the image paths and their corresponding basically label, and column labels, which is going to actually label the columns. This thing is either a list of two items, so it's either image, or at least we only use it as either image and prediction or not at all. As we can see here, since it's empty, If we look in the first line of our function, it says, or second line, this is just a table line equals center. And then after that, if column labels, so if this list, basically Python says if you call if on a list, that would be true if it had any items, and it would be false if it didn't have any items. So if we do actually want to pass column labels, then we just pass column labels. It would automatically go into this if and make the first row to have these corresponding headers that are not here for this one, but for the other one, again, if we submit a file here, then it would show up right here. Okay, so this first line here, which only happens if we do have column labels, we make a TR, we make a table row, and then we make a table header. So this is the first block here. This is this piece right here. In that, we make an H4 with the style is equal to font family Arial. That's just one of my favorite fonts. And then add column labels sub 0. Okay, so column labels sub 0 is just the first label that we want. So in here, we place our text for the image. And then we close our header because that's the text that we wanted. We close our actual table header. So sorry, header's a little ambiguous. When I'm just saying header, I mean the text. And when I say table header, that means the actual spot for that cell, basically, this block here. And then we're going to open up another one. So that's opening up this spot here, another TH. We add H4 with the style of font family Arial, basically the same thing, plus column label sub 1. So that's just the second column label. So first column label, second column label, we close up our header, we close up our, sorry about that, we close up our table header, and we close up our table row. And that makes optionally the first line of the table. Then what we want to do is generate the rest of the table on the fly. So basically we need a bunch of image paths, we need a bunch of text, and don't worry about how we're actually going to obtain these, but in this function just assume that we have them. And so what we'll do is for name and image path, if you haven't seen zip before, basically it just does, if we pass zip with names and image paths, that would go through, and each time in the loop this would be, name here would be the item corresponding to names, and image path would be the item corresponding to image paths. They go through and loop one by one, pairwise through these two things, okay? So S, which is our string that we're going to return at the end, plus equals, we're going to make a new table row for sure. We'll make the first item a TD with an image. We chose a height equal to 80 pixels and a source. So the source right now is going to be slash, and then the image path, which we'll see the specifics later as to what this actual path really is, but we can zoom in for now and see it's really like table here, table body, and table row. Basically, the path is pretty much like this. Static on the main screen, here's our main screen, we're going to make this folder called original, which just has, because if we go to this website, I'm showing you these pictures every single time. And so I've stored, or at least I'm going to store these images in our folder, in our static folder, so that we can serve those to you every single time, the exact same pictures. And that's going to be our paths. That won't change at all. But if we were to then submit stuff, which we'll see how to do shortly, I submit this, we can zoom in on this path, center table, table body, table row, second table row, table, there we go. So static forest1.jpg. Okay, so basically what happened is that puts it in that's going to put it in our static folder, and it'll just show up here, and we'll have memorized the path that we did there. Okay, so I'm just giving you a lot of background information on how we're going to do this, but basically that is the corresponding, that will be the pattern of the corresponding paths that we'll be placing here. But don't worry if that didn't make too much sense. So we add in the source, which is the path, by quote, and then slash single quote. We have to, it's kind of weird when we do this, and you'll see it a lot where we do double quotes and then inside we'll do single quotes, because HTML, you actually have to have the quotes sometimes. Don't worry about the specifics, just kind of copy what I'm doing here and get a feel for it. And then plus image path, and then we add in the quote here, and that has the full path there. So then TD, we close up our spot there, so that closes up this table data, and then we want to stay in the same row, so we still have TR, and then we add in another TD. That's the second spot for the first row, and then the second column here, this spot, we add in a text, and so it's TD with the style is text align center. I'm not sure if we actually need that with that, but I have it in there anyway. Name, so that is the corresponding name, which we want to label that corresponding image. and then we close up that table data, we close up that table row, and then we go through all of those for all the images and the image paths that we have. We're going to iterate through that, produce what we want, and at the end, we're just going to close up that table that we opened up here, and then we're going to return s. So we're not really able to use this function quite yet because we haven't really we aren't able to call it, but hopefully you understand what this does, and we will work on calling this very shortly. Okay, let's work on adding the table to this main screen here. So comparing it to our the app that I've finished over here, we do have this text here. I will quickly add that in as well, and then I want to call this function with the right variables to show these pictures. Well, what are these pictures? Okay, first we actually have to go and grab these pictures. That is from our Colab dataset, and right now probably yours as well, if you've taken a while, has actually just given up on you. So I first need to again upload my kaggle.json API. There it is, and then I need to run that again. And that will automatically do actually all that we need, because it's going to download the dataset, unzip it, and it will have just some data where we can go in and download one of each class that looks like a good representative example that we can show here for all the different categories. Okay, so hopefully that should be done very, very soon. All the streets, I think that's the last one, done. Okay, so we'll just go to segtrain. And actually, I'm just going to grab the first of each of these things. So I'll open up buildings and grab buildings. I'll just say 0.jpg. That should be fine. And take a look at it. There it is. That looks like, I think that's a building, but I don't even know what that is. Yeah, I mean, it has to be a building. Forest is going to be, and that's why it's so great that this model has like 90% accuracy, because the data is a little bit weird. Here, we'll just get the first forest here. And I actually am just doing this to show you what you should be doing. But I already have these in the format that I want them. If I go downloads, I just downloaded one of each of them, and I called it street_1, c_1, and all of these just _1. I don't even think I need the _1, but because we're going to just put them all in their own folder. So if we copy these over to static, in static, we want to make a folder called original. This is just the stuff that we want to actually deploy to the cloud no matter what. This is all the images we are definitely going to serve. And so here we should see them there. If I zoom in a little bit, there we go. We should see the images. Okay, so these are the paths, and the paths are relative to this main.py file. It's going to be /static /original / whatever the type is _1. So those are going to be the corresponding paths that we want to show for our main screen. If we go into our file here, and this is what we'll be calling our table function with, our table HTML, get HTML table down here, we are going to get original paths is equal to, we're just going to do it by hand. So building1.jpg. Notice for now, I'm not worrying about the static thing, just the end, the actual file name itself, building1.jpg, or whatever you happen to call them. It's easiest if you did exactly the same thing. But forest1.jpg, then we have glacier, nope, sorry, I need the quote, glacier.jpg, that should have an _1 as well. We need mountain1.jpg, and notice I am going in the same order, and I'm just going to split this up. I am going in the same order as what's in the class mapping from the dictionary of earlier, but we don't actually need to do that. This is really just a display thing. It makes it easier though. So c1.jpg, and finally we have street1.jpg. And if you actually looked earlier in the video on my site, you may have noticed that these two were actually swapped. I just fixed that recently. Okay, so those are all of our original paths, and then we are going to make really the full path, which is just going to be the static piece in front of it, and static original actually, because we put it in this static original folder as well. Okay, so the full path, and notice exactly how I'm doing this because it is very particular. Full original paths is equal to just static. I'm not putting a slash there. Why am I not putting a slash there? That's because I put it down here, okay? In the table function, I'm starting with a slash, and we don't want 2 slashes there. We don't want 0 slashes there. We want it to be 1//static. So in here, I'm starting with just static / original / plus x for x in original paths. Okay, so that makes this full list exactly the same. It's just this list but with static/original in front of it. And again, when we include it down here, it will have that slash at the beginning as well. Okay, that was just a design decision. You could have obviously moved it up here instead of down there if you prefer that. Okay, so those are all of our original paths. We're pretty much good to pass that into our image paths function or into our HTML table as image paths down there. We'll use that shortly. Now display names. This is going to be the names right here. So we'll call this display names. Could have called it down there as well. It's just going to be whatever we want to call it. So in order, it is, again, this is a building. We need it lined up with that. This is forest. This is going to be a glacier. The next one is a mountain. Then we have, and we could have done this programmatically, but this is fine, sea, and then finally street. Okay, so these are one-to-one mapped with each other with the path and then the name. We can pass this into, if we were to get, actually one more thing, but first I'm going to do column labels. Column labels is equal to just nothing for now, because on this page, this is the slash directory. We just want to get, we do not want any sort of column labels here. It looks fine. So column labels is just this empty list, and then content, I'm going to do this. Content is equal to content plus the get HTML table. So get that table with full original paths. Those are the image paths. Display names. Those are the names. And then just this empty list, it would work totally fine if we just pass that empty list. But to make it clear, column labels. Column labels. Okay, so that's content. We get that content, whatever it was before, plus that HTML table. And then we can go ahead and return content for now. So let's see what this does if we were to boot up our app again. I'm just going to restart that. Go to that link. Here it is. Restart it. And we can see here, please upload your scenes. We'll try to predict which of these categories they are. Building, forest, glacier, mountain, sea, and street. If we were to check the paths, F12, we can see center. And where's the table? There's marquee, H3. Table. I was just being slow. Table body. Each of the table rows, we don't have any column labels. In here we have each of the table datas, and then first we have the image as well with a height and width of 80. Okay, so that's pretty great. That's a big part of our making this pretty. What's missing here between our real app is we don't have this thing to submit, and even if we did, it wouldn't really go anywhere. So we're just going to add in that button that allows us to submit images, and we'll make the pretty HTML for what happens after that, which is really just another call to the table and using our model after that. Okay, so let's add in this functionality with the button. Okay, as usual for the kind of weirder code, I'm just going to paste this in here, which is adding to content some more HTML. Here's the string, and we're going to add some BRs for just line breaks, but then the important part is a form where the action is equal to /upload files/. That should look very similar to up here, where in here we're doing a get. If you do a get method in HTTP to slash, then okay, we're going to do all this and return that HTML. But if you go here, if you click this button, sorry, I went to the wrong spot. If you go here and click this button, then you are going to go to upload files/. And so we're going to need to make a function a lot like this thing, a lot like this piece, except also it needs to accept a post method, because we're going to do a post because we are submitting files. We're giving it data, so we're doing a post method. And we're making this form to do that. So form with action, we go to upload files, we enclose type a multi-part form data, and the method is going to be done with post. So now we're going to include a couple buttons. Input name is equal to files, where type is file, and we're going to allow multiple of them. And then an input type, which is submit. So that really just says, okay, go, and then do this action right here, which is go to /upload files and deal with all of the images. We'll see how to do that with Fast API shortly. It's a little bit weird. But here's the HTML form to do that. This isn't really going to work, but if we were to try and rerun our app here, and we were to give it a go, sorry, I gave you a sneak peek of what would happen. So here it is, choose files. We can see our button does appear down here, and then we submit. But detail not found. It doesn't know what to do because /upload files/ doesn't even, it has no way to catch it. We only have a catch for just /. If we tried anything else like /upload files, it wouldn't find it. So we're gonna have to add it in soon. Something we should also do while we're at it is to get this static files thing. So from fast API.static files, we will import static files with capitals there. And then right under app, we are just going to basically declare that this static files is folder that we used is static. And don't worry too much about what that means. Pretty much just means not going to be changing too much. So we will do app.mount with the directory, so /static. And then what we do is static files with directory is equal to just static, no slash there, so static. And then we do name is equal to, again, just static like that. You won't even see a difference if you were to change it right now, but it will likely help Heroku interpret this properly. Okay, back to the dealing with the problem at hand. We're going to import a couple different things. That's why I was reminded of it. From typing, we are going to import this thing called capital list, which doesn't really have anything to do with Fast API, but it is Fast API is one of few things that actually pretty much require this. And then we are also going to need in the Fast API, this part, after Fast API, we're going to get file and upload file because as you've seen, we're dealing with uploading files now. So this is probably the most complicated piece in the whole tutorial. So hopefully you can get if it doesn't make sense, at least you can just kind of copy and paste what's going on here. But hopefully I can explain it. We are doing an app.post. So that's because we're doing the upload files thing, as we saw way down here. This is method is equal to post because we're sending data. So we need a post here, and then we are going to give this the directory that, or at least the place that it said it was trying to find it, which is upload files. Sorry, I explained that poorly. Basically, here the action is /upload files. So this means, okay, go here, go do this, go to this place, do a post method there. Then we will do set a response class equal to the HTML response as usual. And then we are going to make, again, don't worry about async too much, but an async define create upload files. I don't really know why I have create there, but there's probably a reason. And then we will set this thing called files to be the list of upload file. All right, kind of weird here, but now this files thing is it's basically our files, and we'll look here. The data types gets a little bit confusing, and it's, to be honest, it took a little bit of hacking for me to just get through it, but I'll show you how to make it nice and easy. We set these equal to be file ... which is that thing that we uploaded from Fast API above like that, and then we do colon because this is the definition of a function. Okay. The confusion is about to really start here. So now we have these files things. What we need to do first is kind of read them. So we'll do images, which is bracket bracket, and then we'll do for file in these files. So for going through these files things, it's a list of upload file. We'll do f is equal to await. Don't worry too much about the await part. File.read bracket bracket, and then images.append with f. So then we have a list of these image things. What the heck are they? Well, it's kind of weird. So it's this weird buffered thing, which probably doesn't make much sense. I'm just going to show you how to read from it properly. So we can do from NumPy. We're going to use NumPy to understand it. From NumPy, actually no, we're just going to import NumPy as NP. Import NumPy as NP. And then we're going to read these things into NumPy arrays from buffer. So images is equal to NumPy.fromBuffer. Okay, that's what these kind of f things are. From buffer, where we do image, and they are going to be NumPy.uint8 because we're initially we're being sent pictures. Those are really just a bunch of numbers in a particular arrangement. Okay, so NumPy.fromBuffer image. What is image? Well, we'll see that shortly. NumPy.uint8, and then for image in the images. Okay, so we're just going through each of the images, these things that we have, these files, and then we're changing them to the NumPy.fromBuffer. Specify the data type is uint8 image. Good to go. Okay, so then after that, we are going to read them into actually understand them as NumPy arrays like they are in Google Colab. This is images is equal to cv2 dot imdecode image, and then cv2 dot imread underscore color for image in images. And that is why we need to import CV2. So that's the same OpenCV environment that we had in Colab. I don't know why it's not recognizing this. That's because I called that im. Okay, so now what we did, we read them from buffer into these NumPy arrays things, but to actually decode them properly, we're going to use OpenCV. So we do cv2.im decode the image for all of those images, and the im read color. I don't even know what that is, but you can go look it up if you want to. And then we do images resized is equal to resize the image, which is a function we have not created yet, but we're going to do it very shortly for image in images. And this is because, I'm just sending, you notice how we're doing this is when I click this function here, we're just doing pictures. We're just sending data, and then we don't know what shape it is. This resolution could be whatever, it could be whatever. So we're going to have to reshape it into how our model will recognize that. And so we're going to make this resize function, which is basically just going to call OpenCV very quickly. It's going to be a very small function. It pretty much just converts them to 150 by 150, again by 3. And to copy this function in, it's super easy. We have resize right here, which returns the cv2.resize of the image, and then we resize that into 150 by 150. We do that for all of them. Those are the images resized. Almost done this piece. We are not quite done yet. After that, we have, convert color. Okay, so for each of these images, RGB is equal to the list of cv2.convertColor image, and then cv2.color bgr2 RGB, because as we saw in Colab before, OpenCV reads them in as BGR. Our model doesn't want that, so we convert each of them to RGB, and we'll do that for image in images resized. Okay, that was a long way, and it took me a bit of fighting to get this right, from how to upload images, read them in from the buffer, decode them as NumPy arrays using OpenCV. We need to resize them to make sure they're the right shape. We need to recolor them, at least change up the channels so that it is in the right arrangement. And now we are pretty much ready to incorporate that model that we have, the TF Lite model that we put there a long time ago. We are ready to use that along with our pretty much the same. I hope that we can use the exact same model predict function right here, which uses our TensorFlow Lite model. Okay, before we pass them to our model, I do want to save these files so that both, if we want to, we could actually read them from disk and then we could apply the model to them, but at least we need them saved no matter what, because we want to, as we saw, we want to show back the picture that was sent. So we go here, we choose our files. We actually need to have saved these couple images that we sent so that we can display them as they are like this. Okay, so how do we do that? We're going to use something called Pillow. It's an image library, and so we write it like this. We do from capital PIL import. That's basically Pillow is this PIL thing right here. From PIL we will import image. And so that is pretty much just a way to deal with saving images. We're going to read them in from arrays, which is what they are right now. These are NumPy. Each of these images here in the list are NumPy arrays. We are going to do for image and name. Why are we doing name? Well, I can get names very easily with files. So each of our file names, I can get names is equal to the list of file dot file name for file in files. So this is this files list here. I'm just going to grab each of the file names. That is whatever they happen to be sent as. It's for example, they could be sent as these things, these names right here, except that is not in the right folder. We would be placing them in this main static folder here with whatever we called them. We're just going to put them in this folder and save them with that same exact name. So we get the names, and then we can do for image and name. We saw this before in zip of images, RGB, and names. Okay, so we iterate through both of those things, and we'll say pillow image is equal to the image dot from array. It is array of image. And then we can do pillow image dot save, where we're going to place it in static slash and then plus name. Okay, so we whatever that name was, we're just going to save it in static there, and let's just make sure that that piece itself works. So if we were to rerun our app here, UV main app, and we spin that up, we can see if we go over here, I'm going to make sure that we're going to the root here. Okay, so we're going to upload some files. We'll choose these ones right here. Submit. And okay, it's still going to crash. We're still going to have some weird response here. But what happened? What happened? So if we go to static, we should see Fast API app static. We did save building1.jpg, looks like that, and mountain1.jpg looks like that. Okay, it's a lot smaller, it's a lot lower resolution because we made them 150 by 150, but most importantly, we saved them there so that as long as we keep track of the paths here, then we can return that to the user later as the HTML. Okay, so I'm going to delete those because we don't really need those, but just showing you that that functionality did indeed work as we expected it to. Now what we're going to do is create our interpreter or a model, our TF-Lite model, actually outside of these functions. So we're going to do it right after we initialize the app. We are going to, and actually it doesn't really matter, we can kind of do it before that as well, the model itself. Okay, so what we're going to do here is we're going to import TF-Lite as we saw it before. So this means import TF-Lite runtime.interpreter as TF-Lite. That was the same thing as we did in Colab. It's going to work the same way on Windows here. It claims it doesn't know where it is, but I promise you it will be fine with it. So we can do this above, I believe below or above app. It doesn't really matter. But we're going to do model is equal to TF-Lite dot interpreter, make sure to spell that right, where we give it the path. So static slash mobilenet.tflite is that's actually what I have written. I think ours is model.tflite. Okay, so I'm going to call that model.tflite. Whatever you called your TensorFlow Lite model, and wherever you happen to store it, we're going to load it like that. We, as before, we allocate the tensors, model.allocate tensors, like that. And then we got the input details and the output details. Input details is equal to model.get input details, bracket bracket, output details is equal to model.get the output details. Okay, we are also going to, I'm just going to copy and paste this in. This is our class mapping that we had from before. I'm just going to make it on the fly because if you recall, we kind of generated this automatically from the generator thing. I generated from the generator. But this is exactly what it was, which is just 0 corresponds to building, 1 is forest, 2 is glacier, and so on. Okay. And now that we have all of that, I'm going to copy in our model predict function because it should be just fine to use like this, as long as we formatted our data properly, which we should have. That's what we spent so much time doing over here, was getting them in the right format. I think we still have to convert them to floats before we can call the model predict function, because right now I think they're uint8. And we can probably go ahead and do that right now. Actually, I have a copy and paste for that, which is nice and easy. So here in our images, sorry, that's a control F, that's not right. Images array, I'm just calling it that, is equal to the numpy.array of images RGB. So that is what these things are. And then dtype is equal to numpy.float32. We're just casting that images RGB array into floats. And actually, these are lists. So actually, this should be fine because I wrote numpy.array of images RGB. So yes, that's totally fine with this object being a list, and that should be converting them. Okay, so we've set up our model. Model is this. We load it, we allocate the tensors, we get the input details, we get the output details, we know the class mapping. What do we have to do now? Well, we can do something very similar to what we had before. Sorry, I'm getting a little bit lost. In here, we have images array. And what we could do is get the class indexes, basically. So the indexes is equal to the model underscore predict images array. Why am I calling it class indexes? That is because it is returning, if you take a look at it and remind ourselves, it's returning the argmaxes, which is just the indexes corresponding to what the predict class should be. but we don't actually have the class from that yet. What we need to do is get the class predictions. Class predictions is equal to the list of class mapping sub x for x in class indexes. So what that does is for each of the items in that in those indexes, we convert that using the dictionary, using that class mapping dictionary to get the proper string from it. So that this should be now a list of strings rather than a list of any sort of numbers. So we're really close to done here. What we can now do is get make the column labels, because we are going to be calling our getHTML table function. Column labels, what do we want to label our columns as? We are just going to make it, we'll just write image, and then we will write prediction. We will make the table, get the table HTML. Table HTML is equal to the getHTML table. What are we passing this thing? Well, we need image paths. Do we have those? No. Okay, we don't have image paths. It's really easy to get those. Basically, this is the images list. Right after images, we can actually go ahead and get image paths, which is equal to, so basically here, you can see that we're storing, actually I'll put it here because that makes a little bit more sense. Right here, we are storing it as static / the name, so we can get this this list very easily. We could also have thrown it in an append in this function as well, but I'm just going to get image paths is equal to, it will be, sorry, I'm typing spastically, static / and then plus name for name in names, because names was the list of file names that we had, that we got, or was names, sorry, I lost it. Names is here, so we got all the file names. It's just going to be static / plus the name. Okay, sorry I took a little bit long to explain that. That wasn't quite necessary. Table HTML, not minus, is equal to the get HTML of, what do we pass here? So image paths, we have the paths. Okay, that's great. We have class predictions, because we just got all of those. Class predictions is just the names. Okay, it's just the names that we want to display it, which is the prediction. And then we pass column labels because we actually want these to be the column labels. For now, we will just return the table HTML, and I'm pretty sure we're going to get an error, but we will fix that very shortly. Return table HTML, and from that we get, let me just run this for us. UV main :app, we reboot, we go here to the main screen, and we can submit our files, choose files, forest and mountain, submit, and actually that worked out very well. So mountain and forest, and there's image and prediction, there's our table. Okay, a really easy fix to a lot of the ugly HTML stuff is we can do content is equal to the head HTML. That was that thing that we were using before at the top. And then we are going to add in this marquee, which is very similar to the one for please upload your scenes, but this will be, here's our predictions. And I think that should be, I don't think that should have a space there. Here's our predictions, H1 in the marquee. And then we can do plus the string of the table HTML. I don't think we need string because it should already be a string. But then BR, and then form method equals post action / button type equals submit home. So basically we're just adding in the home button, and so we're doing a post method back to the original thing place here. So we need to be able to do at app.get / and then response class, sorry, not the whole point of that was to write post. So this thing exactly the same, except we're writing post there to allow a post method, because we need to be able to do this now. And so if I write this, it should be a little bit prettier. We restart it, we go, and here I'm actually going to restart the app from the start here. Please upload your scenes, choose files, glacier building, why not, submit. And image prediction, why did we not get our color? I know why, it's because we didn't actually return anything different. So we obviously want to return content. You probably saw that. If not, well then, I caught it first. Just trying to have some fun. So that looks a little bit different, I think, but it doesn't matter. Choose files, glacier, and building. We'll submit that. and that still did not do what I expected it to, so I'm going to diagnose that. Okay, sorry, I didn't actually change any code. All I did was I just reran the app or saved the file or whatever, and it seems to have, the problem seems to have been fixed. So we go to home here. That actually brings us back home. And is there anything else in this application that we're missing? I honestly don't see anything. Choose files, Glacier, and building for fun. Submit. Here's our predictions. Glacier, building. We can go home. And this is the website right here. Everything, building, and forest for fun. We will submit that. Here's our predictions. Looks pretty much the same to me. I can't see any difference. So I guess we are done. Now we are ready to deploy the app, which is, for me, to be honest, I went through a couple iterations of trying to figure stuff out and figure out why it wasn't deploying. For example, there's no way you could have seen coming the whole TensorFlow Lite runtime differences, but I will try to show you as much as I can of the diagnosing process of trying to figure out why it isn't working if you are having troubles, because it's hard to get this right the first time. Let's get started right away by, if you haven't made a Heroku account, you should go to Heroku and make that account, but I am just going to be magically signed in when you see this next. Okay, hopefully you had no problems making an account and signing in. Make sure you use two-factor authentication if they don't force that, but here, we should get to somehow the new create new app screen. And so app name, I'm going to call it basically fast. What have I been using? I'll stick with the same name that I had at the bottom here. Fast API app. We'll see if that's taken. I'm not sure if that's taken or not. Fast API app. Unsurprisingly, already has been taken. So we're going to do -Greg Hogg, and that's probably fine. Okay, app owner is me. That's my email. Please don't look at my email. I guess I'll be having that blurred out. And choose a region is going to be United States is fine. Now that we've created that app, it brings us to this screen. And there's a lot going on here. It says all the things that we need to do. You may want to install the Heroku CLI. We don't have to do that. We are doing GitHub. Okay, so you should be logged in to connect your GitHub account to Heroku, and then you can just search for your repository. So the one that we have here is, where I forget what I called it. What did what did I call it, guys? Fast API app, that's the one. Okay, so I'll connect that application, and by the way, we are unable to access this connect repository. It's either empty. Okay, so the reason it is empty is because we haven't done any commits yet. At least if you've been following along with me entirely, you'll notice that we have not committed absolutely anything. So what this means, we actually have to add specific files. What we're going to add is main.py. Very obviously, that's our actual application app. We're going to need that one. Static slash, all of these things that are static slash, we don't want these, because these are the ones that we're going to be, wow, I didn't know, I actually didn't know GitHub Desktop showed them here. But we don't want static slash stuff, these images, because that's what happens when we upload them. That's just where we happen to be saving them. So I don't want those ones. What I do want is the static slash originals, because that's the ones that we're going to be showing you on the main screen no matter what. I don't need Windows requirements. We will need a requirements very soon. But for now, main.py, we do have the model on there, and it's nice and tiny, which is nice. So we have no problems there. And now we're going to commit pretty much everything we need, but not everything. Okay, so I'm just going to say commit 1 or whatever. If you're making a public app, you may want to make these a little bit prettier for employers, but that's totally fine as it is. So I commit that. That is going to take a little bit of time, because the model is I think it's only 8 megabytes, I forget, but on my internet here, the upload speed is not very good. So I'll talk to you after that's ready, I guess. Okay, that's done. That commit is done. So after I refresh, just hitting F5 here on the Heroku screen, it should see that, yes, it knows where, it can see our GitHub app, because we actually have contents there in GitHub, and then we choose a branch to deploy, which is going to be main. I promise you this won't work as is, because we are not specifying to Heroku what requirements it needs. In fact, it fails very, very quickly, determining which build pack to use, no default language. It doesn't know a lot of this configuration stuff. So I will show you how to make these various files, where I will grab them from my copy here, which you should be able to see. Windows requirements, we don't need that. Runtime says what Python file we need. Okay, so we're going to make a file in right here, fast API app. Actually, I'm just going to go in and delete these very quickly. Building, or forest, glacier, mountain. We don't need those ones. Okay, so here, notice that we have this .environment thing, which is it's 250 megabytes. It's pretty much everything that we need to have this environment on our Windows, our virtual environment. But we do not want to send this off to GitHub. We don't want GitHub to be like, okay, we have this full environment. Here's TensorFlow Lite. Here's OpenCV. We don't want any of that stuff. What we do want is a requirements file that says what we need. That's what Heroku wants. It says, hey, what do we need? For now, we're going to do a runtime.txt, which just specifies the Python version that we're using. But then immediately, we're going to grab the requirements.txt file for the virtual environment. And Heroku actually just pretty much knows by default, and we might have to tell it a little bit more, but it knows that it's like, okay, I see your requirements file. What I'm going to do is just make a virtual environment and install all of those libraries. So not runtime, but requirements.txt, we'll give it that. And then there's one other thing that's just a little bit, this is pretty much just Heroku specific, or at least deploying on web server specific, this proc file. Okay, there's no extension to this file. It is literally called proc file. And so we need to make it here. This, by the way, all needs to be in the same root directory as main.py, requirements, runtime. We don't need the Windows requirements, but I'm going to keep that in our side. And then we are going to do a new file here called the whole thing is just called proc file with a capital P. Yes, I want to change the extension basically to nothing. We need to open this in Notepad, and we paste in this thing here, which says, hey, it's a web app. We're going to use G-Unicorn, which is, I don't really even know all of these different letters. This is just what we need for Heroku to make it work. Web G-Unicorn -w3-k unicorn.workers.unicorn-worker main app. Okay, here's the part that we recognize, which is a slight change from unicorn to unicorn worker main app. Make sure in particular this stuff matches your setup if you did try to do it, choose to do it a little bit differently. Okay, so there's our proc file, and then and that should be probably good to go. There may or may not be one thing that we need to do, and I'm gonna find out now if it's actually something I require or not. That definitely, okay, what I didn't mean to do is I did really mean to submit all of these files to GitHub itself, so we definitely have to push proc file requirements and runtime, and I will just give it a summary of added web specific requirements, commit to main, and we will push that. And there we go. Okay, so we're just going to refresh that to make sure that it gets the updated version from GitHub, and we are going to deploy the branch. And I'm going to watch this one with you to see if there's something else we need. Determining which build pack to use for this app. Python app detected using Python version specified in runtime.txt. It says it wants us to use 3.7.12, but we're not. That's totally fine. You can choose to do that if you want. I'm sure it'd be fine. It knows to install requirements with pip. It does all of this stuff. And now is a really good time for us to look into a little bit about what's in this requirements file. So what is in this requirements file? Well, a bunch of stuff, but the important, there's some important pieces here which you might have not considered. So TF Lite runtime, that's we saw that one. Another really interesting one is this headless piece. So if you go to pip install OpenCV in your normal environment, it's going to not get this headless thing. And that's because it includes a bunch of other stuff that you might want to use for development, for actually going and using OpenCV, and even for, of course, for some applications that you might want to write, you might need the full OpenCV library. But we really don't. We just need the tiniest little bit from it to do some image manipulation. And so we can get by with this headless thing. And any way to make less disk space or memory requirements on, or like main memory requirements on Heroku is very, very ideal. Notice how fast it deployed. If we put full TensorFlow and OpenCV on there, it would have been way bigger. In fact, it wouldn't even have worked. And it took me a long time to shrink all of the stuff down to get it totally for free. So it's free. We go to deploy the app. Please upload your scenes. Let's see if it works. Choose files. We'll choose a building and a glacier. We will submit those files very quickly. Go. It got sent. Here's our predictions. Glacier, building. Clearly our TensorFlow Lite model is working. Clearly our website is working. We go home. This is free. you can build this right now. Please go ahead and do that if you didn't already. If you did build it alongside me, congrats, because this is an amazing project. I'm sure you learned a lot. And let me know if you do run into any difficulties. I hope I can try and help you out with those if they're things that I can understand really quickly in the comments. But again, if this helped you out, I'd really appreciate dropping a like. If you're not subscribed yet, come on. This earned a subscribe. I hope. Anyways, no, I really hope this helped you out. It's a really great project, and I really hope to see you in the comments. Drop a comment down below, and I'll see you next time, guys.